Hello, I'm Gaia Paolini, and I'm a data scientist at Spotfire. Welcome to a presentation about explainability and model monitoring.
And I am Marcus Horbach, data scientist at IBI.
As a reminder, all information and presentation here is a property of Spotfire software.
The purpose of our presentation is twofold. Primarily, we will focus on our ideas about model explainability and model monitoring. But we will also discuss our new way to make such and other functionalities available, namely by means of the new data science and machine learning toolkit for Python, or DSML Toolkit. This toolkit is a Python package that consists of functions in several modules for various purposes. The modules are built upon familiar packages like scikit-learn, XGBoost, TensorFlow, Pandas, NumPy, etc. Functionality from the package can be imported into any Python code, for instance, Spotfire Python data functions. The merit of this package is that its functions are well aligned with logical tasks, de-emphasizing the underlying technical tasks, thus making it easier for you to quickly and robustly develop non-trivial Python code for machine learning purposes. For instance, one of these modules, ML modeling, is dedicated to training and evaluating regression and binary classification models with just a few function calls, as you will see in some detail in a moment. Other modules in the package deal with model explainability and model monitoring. We will talk about them as well. A central notion in our machine learning related modules is the pipeline model. A pipeline model not only contains a classifier or a regressor, it contains embedded in it all the data pre-processing steps needed to deal with non-numeric data and with missing data. Pipeline models can easily be saved and loaded as one object. For instance, you can train the model in one Spotfire application, save it, and load it into your deployment environment, which may be another Spotfire application, and use it there without getting into any data pre-processing troubles. Going forward, this DSML toolkit will be the means by which we offer various pieces of functionality in a product-independent manner. This way, the functionality will be available to all our products that allow for developing custom Python code, and even in your own standalone Python environment. Now, in order to discuss our ideas about model explainability and model monitoring, we will use a model which we will train and evaluate using the ML modeling module. Specifically, we will focus on the case of a bank that wants to identify customers that are at risk of churning and wants to understand why these customers are at risk in order to be able to take targeted preemptive action. Given a data set with historical data about its customers, including a label that indicates whether the customer has churned or not, this is a binary classification problem. This piece of code shows how to train a binary classification pipeline model and evaluate its performance. We here assume you have already done the usual train test split of your data and that the data is stored in Pandas data frames. To use the functionality from the ML modeling module, you need to import it from Spotfire DSML. You define a standard pipeline by calling the function createClassificationPipeline from this module. It creates a pipeline that separately pre-processes numeric and non-numeric data, imputes missing data, and sends the pre-processed data to a random forest classifier. Without going too much into details, you have options here, in particular about the encodings of the non-numeric variables, and you also have the choice from a number of classification algorithms: random forest, XGBoost, logistic regression, neural net, and you have the option to specify their hyperparameters or accept the defaults. You train the pipeline on the training data with another function call. In case you train an XGBoost classifier, early stopping is used in order to avoid overfitting. You also have a function to do hyperparameter optimization using a grid search. The performance of the trained model can be evaluated using the test data with one function call, and feature importances can be computed likewise using the permutation importances method. When this code is inside a Spotfire Python data function, the results can easily be sent back to Spotfire to be visualized, as you see here. This is a pretty complete evaluation of a binary classifier. You see the ROC curve, a precision recall curve. We compute the F1 optimal decision threshold, confusion matrix, and the usual performance metrics derived from the confusion matrix: accuracy, precision, recall, F1 score. The histogram of predicted probability tells you something about the resoluteness of the classifier. The feature importances on the right give insight into what in aggregate are the most influential features. Note that this does not mean that for each model outcome, these are the most important inputs. It is just on aggregate. We will come back to this point in a moment when we discuss explainability. So now that we have a good model, we want to use it, that is, to make predictions on new data. However, just making predictions often is not the end of the story, and this is where model explainability and model monitoring play a role. Machine learning models are increasingly being used for making decisions in situations that directly affect humans. Examples are financial, legal, medical settings. Naturally, this raises questions about accountability and trust. Therefore, it's not only desirable to provide supporting information about a model outcome, it may in fact well be illegal not to provide it, as formulated in various forms of right of explanation legislation. In such situations, it is clear that explanations can be meaningful to the recipient of the model outcome only when they refrain from referring to model internals, its mathematical structure and parameters. Thus, the model must be treated as a black box. In other words, the explanations must be model agnostic. The only quantities that then are available from which to build a useful explanation are the instance-specific model inputs and possibly insights about the larger pool of instances from which this instance is a member. There exist several methods that produce such single instance explanations, also called local explanations. Well known are SHAP and LIME, which require numeric input features. We have developed an alternative named XWin that works with numeric and non-numeric features. XWin stands for explanations from the impact of withholding information. The idea is simple. To assess the importance of an input feature for a particular model outcome, we measure how much the model outcome changes if we substitute the feature's value with a missing value. That is, if we withhold the feature's value. The pipeline's imputer will take care of the missing value as it has learned during the training. We call the change in the model outcome due to this withholding of a feature value the XWin impact value of the feature. The larger the impact value, the more influential the feature is for this particular model outcome. This works for both numeric and non-numeric features. In a bit more detail, we have an instance and a model outcome for that instance. We repeatedly modify the instance by replacing one feature value by missing and have the model produce new outcomes for the modified instances. The differences between the actual model outcome and the ones obtained by withholding a feature's value are the XWin impact values of the features. This way we compute an XWin impact table of features and impact values. XWin asks the question, if I had withheld certain information, how would it have affected the model outcome? XWin therefore gives meaningful explanations whenever this question is a meaningful question to ask. Going back to the bank churners case, for instance, here's a customer that is predicted by the pipeline model that we just trained to be at high risk of churning with a probability of 0.91, and the bank wants to better understand why. Again, all we have to do is call a function from our new Python package, now from the ML explain module, to compute the XWin impact table. which contains, as I said, the features and their impact values for this specific instance. Besides the XWin impact values, it also returns some other information. Specifically, it returns relative feature values that indicate whether the value of a feature for this instance is on the low side or on the high side, measured against the training data. It gets this information about the training data from an input metadata JSON that contains summary statistics of the training data. Gaia will say more about how to compute this during training and its availability in the prediction environment. Also, an English language sentence is generated, like the one on top. The low value of total transaction count, 39, increases the model prediction by 0.55. This calculated impact table can be visualized by a bar plot, like here in Spotfire. We have one bar per feature. The length and direction of the bars are the XWin impact values, which can be positive or negative, and the color of the bars indicate the relative feature value. The tooltip can be configured to show the English language sentence for each feature. You see again that the low value of total transaction count, it is blue, has a large effect. The bar is long. It increases the probability of churn. The bar points to the right for this particular customer. Once you have this functionality for identifying the most influential input features for a specific model prediction, you can do more. You can explore ways to take preemptive action. For example, in order to see what room there is to improve undesirable model outcomes, you can examine the effect of modifying the values of the most influential features. Again, we look at the bank customer with a 0.9 churn probability. The top influential feature is total transaction count with an actual value of 39 and with a training data range from 10 to 139. You can modify the actual input value to see how it affects the model outcome. This is what you generally do to investigate how to get a more favorable model outcome, probably combining modifications of the few top influential features. Explainability is not only useful during actual deployment, it can also be used during the training as an enhanced kind of feature importances, useful to better understand the model's thinking. Remember, conventional feature importances are statements about the importance of the features on aggregate. On the left, you see the feature importances computed for our model. You've seen this before when we did the model evaluation. On the right, you see the XWin impact values for a random selection of 100 instances of the training data. This gives a more detailed picture than the feature importances do. The features are listed vertically and the XWin impact values horizontally. The 100 impact values per feature, one per instance, are plotted as squares, and the colors of the squares indicate the relative feature values. You see, for instance, that the low values of total transaction count, the top feature, the low values, the blue ones, tend to have a positive impact. That is, they tend to increase the model outcome, while the high values of total transaction count, the red ones, tend to have a negative impact. That is, they tend to decrease the model outcome, here the churn probability. You see such a simple red-blue pattern for most features, which is in fact indicative of there being a relatively straight decision boundary between the churners and the non-churners in the data set. With more complicated decision boundaries, the patterns can be more complicated. This is the kind of insights you can get about your model using explainability. And just as for the single XWin impact table, these batch-win XWin results are computed by one call to a function in the ML explain module of our new package. So far for explainability, Gaia will now discuss model monitoring.
Okay, thank you, Marcus. So let's look at why we would like to monitor our models. When a model is first trained, it's trained on historical data, and that represents the world as the model sees it. But with time, the world changes, data changes, but the model stays the same. So it's very likely the models become less useful over time. And this carries a variety of risks. For instance, we might lose money because we fail to detect fraud. or we might be unfair to somebody denying a loan when there was no reason to do so. So the question is, can we spot the right time to retrain a model? Can we reach a balance between the cost of retraining the model and the consequences of doing nothing or keeping the model as it is forever? There are two main scenarios here we can consider in terms of model monitoring. If the new data is appearing, is soon labeled, so we know what happened, the ground truth, for instance, was it actually fraud or was the loan justified, then we can go ahead and monitor the performance of the model using metrics like accuracy, for instance. But we might not be that lucky, maybe because of the data volumes, the data speed, or the type of problem is not always possible to get the real answer in time when we want it. So we concentrated on the scenario in which the data is not labeled, so we don't know what the right answer is, but all we have is the new data and the model predictions on these new data, and we want to find out whether we can detect anything odd going on. So we're looking for clues. As a reminder, as I said, there's no label, so there is no direct performance metric, where we can find ways of detecting changes, detecting deviations either from the data itself or on the way that the model reacts to the data. So in the beginning, we collect what we call baseline information, which is information about the original training data or the initial performance and results from the model when it is first trained. And then at each point in time in which a new data batch becomes available, we score the data with the model, and we apply a number of metrics which are measured that we use to quantify the deviation. And then when we monitor these changes over set points in time, over a period of time, we get an idea of what is going on. Now, I mentioned baseline information. We also call it metadata because we assume that we don't necessarily have the training data set. It might be too big, or there might be security concerns. But what we store instead are information about this data. It could be, for instance, for a categorical variable, the frequency distribution of that variable, or a binned continuous variable, correlation of pairs variables, or descriptive pairs of variables, or descriptive statistics on the data, as we show on the left here as an example. We also encapsulate the information about the model in terms of the initial predictions. Here we see a prediction distribution, or the variable importance of the model on the first data set. And this information is modular, so if we find new metrics, new measures that we think are worth adding, we can add to it quite simply the way the code is written. And it's also compact because all the information is encapsulated into JSON objects, which can then be shared across systems. For drift metrics, we do something similar. We look for ways of expressing with numbers the difference between two data sets. And again, if we find new metrics in time, we can always add them to increase the detective power of our methods. When choosing the right metrics to apply, for instance, we wanted to minimize false positives because not changes in the data are necessarily bad for the model. We also want to minimize the sensitivity to the size of the sample, but we need to keep in mind that there has to be some kind of reasonable minimal sample size because this is statistical information, for instance, about data distributions. And we want to combine the metrics whenever possible, whenever for instance, there are metrics that apply to a single variable or metrics that apply to the data set as a whole. In terms of using these tools, we have different modules. There's a metadata module in the DSML Toolkit to generate the JSON object that contains the metadata about the data. Similarly, we can generate the metadata about the model, and then we input this tool at each point in time in which a new data set becomes available to calculate the drift metrics in a few simple calls. Now we're going to show a practical example with the same data set that Marcus described earlier, this bank churners data set. And this is our data set 0, if you like. But then we also generated 24 synthetic data sets at 24 time steps with increasing data drift, something that we decided to add as an indication of drift. It could be some slow drift, so-called wear and tear of the data, for instance, changes in the data due to inflation, or some more sharp changes in the data at particular time steps, and we attribute these to possible data collection issues. We also trained 3 predictive models, and we loaded everything into Spotfire and used the Spotfire DSML Python package via data functions in Spotfire to detect the drift. So let's start with showing some results for variable drift. Here in this plot, you see the time steps going from 0 to the top left, on the top left, to 24 on the bottom right. Each bar represents a variable, and the height of the bar represents the variable drift, a deviation from baseline. And you can see that at time greater than 0, some drift in some variables is slowly building. For instance, in the pink variable, which corresponds to the number of times a customer contacted support, this goes slightly up because artificially introduced more customer reps answering the calls, and therefore more calls were answered and more counts were generated. But then we see also a more sharp drift on time step 16, and this is due to the fact that normally the number of times the counts happen counting every 12 months, and because a mistake was made, a fictitious mistake was made, this time period increased to 18 months, and therefore the counts are larger, and this also affects the variable in red shown here. So we can see that there's an accumulation of both slowly varying and more abrupt drift, which is nicely detected by the system. Similarly, in a similar plot, we show drift in the model predictions. Here, again, we go from top left time 0 with the original data set to bottom right time 24. And this plot represents the prediction probability for a customer to churn using one of the models we trained, a random forest model. And we can see that at the beginning, there's neat division across the class boundary between churners and not churners. And this slowly goes down until at time 16, it looks almost completely squashed, and there's an accumulation of responses around the class divider, showing that the model is becoming less resolute. And this is shown on the right in the prediction drift matrix, where the x-axis is the time step and the y-axis is the numeric representation of this drift. And we see there is a sharp increase at time step 16, which is capturing what's happening here. To summarize, these are possible results we can get. For instance, all the variable drift rolled into one in this left plot. Usually we always have the time step running on the x-axis and the drift measure on the y-axis. And there's also something quite interesting. There's a comparison between the 3 models we trained, and these are ordered from left to right in order of the initial performance of the model. So the gradient boost was more performant than the random forest, and which is more performant than the logistic regression at time 0. But you can see that the drift is actually different in the 3 models. And as we've seen before, the random forest seems to be quite affected by the change in the data set. This is not a generic statement around random forest, because the behavior of the model with respect to the data set will depend on the specific data set and the specific problem, the number of important variables, and also the shape of the class boundary, for instance. But it's interesting to note that it's not just important when training the model to get the best model at the time, it's also important to see how robust this model is going to prove itself during time. So this concludes our presentation. Thank you very much. We hope we enjoyed it and got a few ideas about how to use explainability and drift metrics to monitor your models. And we also hope that you are interested in our continued development of the DSML Python toolkit. So please follow our progress on the community. Thank you.